Okay, I want to start off this section with a review. It turns out these three differential equations are going to come up a lot in the next few sections, so let's just talk about them real quick. Any one of these three differential equations, y double prime equals 0, y double prime plus alpha squared y is 0, or minus, all of these we should be able to solve just by using our auxiliary equation, since they all have constant coefficients. And so your answers from the auxiliary equation would be m is 0 and 0 again, which ends up giving you c1 e to the 0x and c2x e to the 0x. Here we get m is plus or minus alpha I, which would be two imaginary solutions, sines and cosines. And here we'd have m is plus or minus alpha, which would be exponential with alpha, exponential with minus alpha. We can also write that in terms of cosh and sinh, but I'm probably just going to err on the side of using exponentials. The book actually does use cosh and sinh about half the time, a little bit more than half the time. Okay, so let's look at something new. So let L be a positive constant, and I'm going to look at the boundary value problem y double prime plus lambda y equals 0, y of 0 equals 0, y of L equals 0. So L is going to be a fixed number. It's going to be the same, but lambda is going to potentially be different. So as you can see with this example or the review up at the top, if lambda was equal to 0, we would expect to have an answer that looks like this. If lambda was positive, we would expect to have an answer that looks like this, and so on. So depending on the lambda, our answers are going to look very different. So let's look at a couple of examples. So let's look at lambda equals -4. Okay, so this is actually going to be y double prime minus 2 squared lambda equals 0. And so by what we already have written at the top, our answers are going to be exponentials e to the 2x and e to the minus 2x. And it wouldn't hurt to just go ahead and do the auxiliary equation every time instead of trying to memorize these rules. Anyway, so that's going to be our general solution, but we have initial conditions we still have to plug in, so let's try those. Y of 0 should be 0, but it's also c1 e to the 0 plus c2 e to the 0. Okay, y of L is going to be c1 e to the 2l plus c2 e to the minus 2l, also supposed to be 0. So let's see, I think I'll try and solve this using substitution. I'll say c2 is minus c1, which means that this equation is c1 e to the 2l minus c1 e to the minus 2l. Okay, moral of the story of this whole section, factoring is your friend. If I factor this on the right, we have c1 times exponential minus exponential. And if I stare at this exponential minus exponential, the only way for, if we have something that's factored equals 0, then either c1 is equal to 0 or e to the 2l minus e to the minus 2l is equal to 0, which would mean e to the 2l is equal to e to the minus 2l. But if you think about it, an exponential e to the x and an exponential e to the minus x, the only time those two are going to be the same is when we have 0. So realistically, the only way for this to happen is if both of them have exponent 0. But the original problem says L is a positive constant, so I guess that's impossible. So if this case can't happen, then I guess this case must be what happens. Again, factoring is your friend. You're going to be trying to break things into cases so you can make some kind of conclusion. We've figured out this case is impossible, so it must be that c1 is 0, which means, according to this equation, c2 is also going to be 0. And so our solution is actually y equals 0. Okay. I'm going to slide up a little bit. That's a little boring. Lambda equals -4, and we got kind of a trivial solution. We only got 0 as a solution. Let's try a different value of lambda. So I'm going to try lambda is equal to pi squared divided by L squared. much more complicated, but let's try it out. So I'm going to plug back into y double prime plus lambda y equals 0. Okay, if you find your auxiliary equation, m squared plus lambda, this constant, is equal to 0, m is going to be square root of minus this, which means m is plus or minus pi over L times I. You get imaginary solutions, which means cosines and sines. So y is equal to C1 cosine pi over L times x plus C2 sine pi over L times x. Okay, let's try the initial conditions. Y of 0 is supposed to be 0, which would be C1 cosine of 0 plus C2 sine of 0, which tells me that C1 is equal to 0. Okay. Other initial condition, y of L is supposed to be 0. So let's see, C1 is 0 cosine of pi over L times L plus C2 sine of pi over L times L. I just went ahead and plugged in 0 for my C1. Let's see, so that's 0 times something. And this is sine of pi. Okay, sine of pi is a 0, so the whole right-hand side is 0. 0 equals 0. Not particularly helpful, but I guess that means there's no constraints on C2. As any C2 I plug in will make both boundary conditions true. So I guess that means our solution is going to be y is equal to a constant times sine of pi x over L. Okay, so what that means is, if you look back at our two examples, lambda equals minus 4 is kind of a boring value of lambda. We only get the trivial solution. Versus this value of lambda, this more complicated value of lambda, actually gave us a non-trivial solution. And so when that happens, when a value of lambda gives us a non-trivial solution, we say that this is a special value of lambda, which is called an eigenvalue. Specifically, it's called an eigenvalue of the differential equation. And then this corresponding answer is called an eigenfunction. Okay, so I haven't written down the definition in words, but the idea is if a value of lambda gives us an interesting, a non-zero solution, we call it an eigenvalue. If it just gives us a trivial solution, we don't call it an eigenvalue. So this is not an eigenvalue.